We've been talking about conservation laws in physics. The point of conserved quantities is to look at a system before and after an interaction and look how a particular quantity has changed from before and after an interaction to see how other quantities like the velocity or other types of indicators of motion have changed, even though we can't track details about the forces during that time of interaction between one or more objects. So we talked about momentum, we talked about impulse acting on momentum, we talked about a system of objects in which there was no external impulse acting on the system of objects, and therefore the momentum was conserved for the whole system, so objects could trade momentum between themselves, but the total momentum of the system didn't change. There are other conserved quantities in physics. The other one we want to talk about in our unit is energy. Now, kind of like momentum, it's hard to give a definition in words that is sufficient, and it's hard to give a definition in words that is sufficient and satisfying for energy. It's a quantity that can be tracked, that we have equations for different kinds of energy, and so it quantifies the state, the motion, the positions, the interactions of objects. But what is it? That's a good question. Some textbooks give this circular reasoning sort of definition, like energy is the capacity to do work. But what is work? Well, it's a transfer of energy between systems through mechanical means. So if you have energy defined in terms of work, and you have work defined in terms of energy, and so it doesn't help you at all. So, we're going to leave a little vague about what exactly energy is in the grand scheme of things. We're going to think of it as a quantity that describes the state of a system or the state of motion of a system. And we're going to end up with exact equations that can be measured for an individual object or system. And then when we add those together, that will tell us about the energy of a system. So, what do we mean when we say energy is conserved? Well, if we think of energy as, let's say, a currency that describes interaction with a system. So, if we have some energy or a currency, so this is the energy of a system, the only way that that energy can change is if energy goes out or energy comes in, right? Well, there are only two ways that energy can go out or energy can come in. One way it can go out is called work. The other way it can go out is called heat. Work is a mechanical transfer of energy, so that means that there are forces involved. And heat is a thermal transfer of energy, which means there are different temperatures involved. There, on this side, transfers into our system are still called work and heat. Work gets the variable name W, which makes sense. And heat gets the variable name Q, which stands for quantity of heat, I think. So, what can you do about it? We, in this unit, will not be worrying about heat. That is for thermodynamics, which is a different unit in the book. So we are only going to worry about mechanical transfers of energy, and those are work. So let's identify different kinds of energy that we can have inside our system, and then we'll worry about how work can change those types of energy. So, the first type of energy in our system is kinetic energy, which is the energy stored in the motion of an object. The next is potential energy, which is the stored in position or arrangement of objects in a system. So, stored in the position or arrangement. So that is a general definition of potential energy. But we have two specific forms of potential energy that we would normally study in this unit. The first is gravitational potential energy. So this is stored in the height of an object. We are going to be more specific about that later. I'm going to leave it like that. And then we have elastic or spring potential energy, which is stored in stretching or compressing spring. Now, this semester, we are not going to worry about that one too much. Normally, we would. There are other types of potential energy, particularly electrostatic potential energy, but that is for another semester of physics. There are other types of energy we would worry about. Chemical energy is the energy stored in chemical bonds, for example. That energy can be released. For example, if you burn fuel, then that chemical energy is released, and it can be released in a number of ways, right? You think of it as being released as heat, but it also drives your car forward, right? So that energy is being released as kinetic energy. And then there's also thermal energy. And so this is energy stored in the temperature of a substance. Now, thermal energy sounds a lot like heat, and this is a very common confounding notion in physics. We are using these words in technical ways. Thermal energy is the energy inside our system. It's the energy inside this box that's relating to the temperature of an object. Heat is when it goes inside or outside of our system. It passes through the boundaries of our box. So it's the transfer of that energy because of a difference of temperature. So it's related, but it's not the same thing. And it's important that it's not the same thing because that transfer of heat energy could be due to something that's not just thermal energy. So for example, you know that if you rub your hands together, right, that makes them warm, right? So that kinetic energy is turning into thermal energy, right? But if you let them open to the air, that kinetic energy you can think of as being released as heat. So there's I think I might just cut that out. So anyway, so there is a transformation between the different types of energy in a system. So anytime you have multiple types of energy in a system, which you often do, you can transfer in between those types of energy in a system. There is one caveat to that, which is you can go back and forth between kinetic and potential and chemical. These can go back and forth in various ways, but thermodynamics tells us if you go into thermal, you are stuck. So you can only release that as heat. And then that heat could then go into another box, and that could become kinetic energy in another box. But that is for another semester. Okay. So we have basically discussed this. There is one additional thing we need to talk about. In momentum, the system was only the objects that were moving that we cared about. There is a little addition here. Now we're going to have to include objects in our system that are the agents of potential energy storage. In particular, the gravitational potential energy, what's the agent of the gravity? It's the Earth, right? So the Earth is going to have to be inside our system. We'll see more about that in a little bit. So let's talk about this box and how it pertains to energy being conserved. Well, if energy can only change if it goes inside or outside of our box, then the change of energy is going to be equal to the work coming in minus the work going out. We call the work coming in minus the work going out, we just call that overall the work. And we know that if it's positive, the overall effect is more work coming in than going out. And then obviously if it's negative, it's the opposite. Okay? So, our most general equation is delta E equals W. And you could put, technically, there's a plus Q here, right? But we are just not doing that this semester. So we're dealing with delta E plus W. So what happens if W is equal to 0? Well, in that case, delta E is equal to 0, right? So that means when you're looking at all of these transformations of energy, they go back and forth between one another, but the total energy of our whole system doesn't change. The total energy at the beginning is equal to the total energy at the end, and we say energy is conserved. Okay? So we will look at these notions as we continue, but the next thing we're going to do is to calculate W and see how it affects a particular system.